welcome. In this video, we will be taking a look at more derivative rules. In our derivative rules part 2, we'll primarily look at some more chain rule, but we'll also take a look at involving quotient rule and power rules as well. So let's dive into the first example. We'll walk through a number of them in this video. So part A, we'd like to find the derivative of the following functions with the chain rule. So g of x is the first one we're going to do. We would note the derivative function there as g prime of x. And then we can consider the chain rule. So if I consider the chain rule on this, we notice that we have some function inside raised to the 7th power. So one way we can apply the chain rule is just by considering the generalized rule. If I have any function and I take a look at that function of x raised to some n power, so let's just say there's a function u, where u is a function of x raised to the n power. With that generalized power rule, we could say that this is going to be n times u raised to the n minus 1 times u prime, whatever that u function happens to be. Move myself out of the way. So that's really the generalized chain rule there, or the generalized power rule for this function here. So in this case, we could write this is 7, bringing down the power, raising the function to the 6th power, and then taking the derivative of that inner function. In this case, it happens to be 6x minus 1. Okay, so that would be our g prime of x in part A. We can continue with part B here. This one's a little more complex because here we have kind of two parts to the chain rule, really two links to the chain, additional links. So we have the natural log of 3 raised to x squared minus plus 3x minus 4. So let's consider diving into this one. We would call this general derivative f prime. And so we really have kind of, again, 3 links to this chain instead of just 2. So we can consider ln, we can consider 3, and we can consider our exponent. So let's consider from the outside in. If I wanted to consider the derivative of any natural log function, I can say, well, I'm going to rewrite whatever's inside my natural log over 1, and then we'll have to take the derivative of what's inside. So let's take that outer derivative. That would be 1 over the inside stuff in the natural log. Times, here I'll write it more generally because we'll do a couple lines here. That would be the derivative of the inside stuff. So that would be the derivative of 3 raised to the x squared plus 3x minus 4. Okay, so we have the outer derivative, and then the current inner derivative is the derivative of 3 raised to the x squared plus 3x minus 4. Now let's write another line here. We'll just kind of come underneath this and consider what would be the derivative of that function, that exponential function. Well, let's first just rewrite our first piece of the chain. Times, well, if I want to take an exponential's derivative, I would rewrite the exponential first, and then take the derivative, or take the natural log of the base. And in this case, we have a chain rule to be happening here as well. So the first thing, again, we would say rewrite our exponential times the natural log of the base times here the derivative of the exponent. And I'll write it out one more time, the derivative of the inner function. In this case, the inner function happens to be the x squared plus 3x minus 4. That would be the true derivative of that exponential function as it sits there. So I have one more inner derivative to take now, and we can kind of see how this is going to simplify as we go here. So let maybe make one simplification. Notice that the exponentials here will actually simplify when I work it out this way. The 3's raised to that polynomial. And I'll be left with here ln of 3 times the derivative of that final exponent, which happens to be 2x plus 3. So this actually is going to be our final result for that derivative. It's just going to be the natural log of 3 times 2x plus 3. So that would be kind of 2 chain links in that derivative. The next one, we're going to consider a chain rule within a quotient rule here. So let's begin with, again, the concept of the quotient rule. So the first thing that we would want to consider is we do have a kind of a chain rule going on in the numerator function. And we also have a function in the denominator. We'll have this, really we could rewrite here if we wanted to just get it started with a 1/2 power in the exponent. So if we rewrote this, we could say this is 4x plus 7 raised to the 1/2. That might be helpful later on. And then we have x squared plus 5x. So really we have kind of a power rule and then in the denominator, and then a chain rule in the numerator that we would want to take care of. So let's start with that quotient rule to begin with. So normally our quotient rule in terms of denominators and numerators is we would want to take the derivative of the numerator. So that would be, we call that n prime times the denominator minus n times denominator prime. And then finally denominator squared. So that's kind of the general rule for a quotient. So here, let's take that same application, y prime here. We'll start with the numerator prime. In this case, we would say that's going to be 1/2 times 4x plus 7 raised to the negative 1/2 times, this is a chain rule, we'd want to take the inner derivative, and that inner derivative is the derivative of 4x plus 7. So that would be a 4. So that's the derivative of my numerator. I want to take this, multiply by my denominator. Subtract the numerator. Times derivative of the denominator. So that would be 2x plus 5. And then all of that is to be divided by x squared plus 5x, quantity squared. So there's certainly a little bit of simplification you could do here, but this is the derivative, and that would be complete just like that if you would like. So that would have really a quotient rule, and then we have a chain rule application in the numerator function. Part D looks at another chain rule dealing with a square root function. And so let's consider this one as well. Whenever we see a square root, again, that's really a 1/2 power going on. So let's just rewrite that here first before we dive into the derivative. We'll raise all this function to the 1/2 power. So overall here we have kind of a chain rule to work out. So we could say h prime here of x. We can bring that 1/2 power down on the outer derivative and raise my function inside to the negative -1/2. And then we have to concern ourselves with the inner derivative. So if I consider that inner function, I want to take the derivative of 2x cubed plus 3x raised to the x squared. So this inner derivative function, we would start with first 6x squared. That's the first term. And then times, we'll have 3 as a constant multiplier. If we take the derivative of e raised to the x squared, well, this is another chain rule in itself because it's an exponential raised to a function of x. So with an exponential, we would want to rewrite our exponential and take a derivative of the inner function, which happens to be the exponent. So that would be 2x. So that would be the complete derivative of the overall inner function there. 6x squared plus 3 e to the x squared times 2x. If we wanted to simplify this a little further, we can. And I'll just simplify this. We have some space here to kind of rewrite this a little cleaner. We can take a look at simplifying the numerator term. First, this denominator is going to have a 2 with the 1/2. And we could bring down our original square root here with the negative 1/2 power. In the denominator, we'll have the square root of 2x cubed plus 3x raised to the x squared. That looks great. And then we can bring the numerator term, that's going to be that last portion. We'll write that as 6x squared. And then we can have also a plus 6x e raised to the x squared if we multiply our 2 and our 3 here. Looks like we might be able to reduce this one more time if you wanted to. And since it's pretty clear to divide numerator and denominator by 2 here, we can just try that. So we'll have 6, the 6 becomes a 3. We'll just cancel out these factors of 2. And we'll be left with 3x squared plus 3x e raised to the x squared, and then our square root in the denominator. So that would be a complete h prime of x. Part E, here's another example for a chain rule, and this is in terms of a product rule, really. There's a product rule, and one of those terms really has a natural log of another function. So this is a good practice with a product and quotient, or excuse me, a product and a chain rule working together. So I have one function, which is the 4x, and a second function, which is the natural log function. So let's take a look at f prime of x. if I wanted to consider a f prime function, both of these we could call maybe an h and a g function if you wanted to write it like that. We would say that the derivative of some h times a g function we could rewrite as h prime g plus hg prime. So that's one way we could rewrite our product rule with two functions. So let's consider doing it just with this pattern. We know we're going to take the derivative of the first, which is 4, times the second, and then plus the first, which is 4x, times the derivative of the second. This is the derivative of the natural log function. We would start out with just the 1 over our argument to that natural log. So that's the inner function, 5x squared plus 7. That would be the outer derivative, multiplied by the derivative of the inner function, which is kind of the chain piece. So the derivative of 5x squared plus 7 would just give us 10x. And that would be the complete derivative of kind of the g function prime. If we wanted to just rewrite this one more time, you can. Just to clean it up a little bit, f prime of x is going to be 4 natural log 5x squared plus 7. And then you have the 10 and the 4, 10x and 4x give you 40x squared divided by the 5x squared plus 7. So we can leave that as such and call that derivative good. So there's a product rule with a chain rule piece involved. We'll continue working through a few more examples. This next page considers a little bit of a different type of example where we are given some functional values and derivative values at a specific point, -3, and we want to use our derivative rules to consider the derivative at the point. So let's consider the first one. We have a, which is f times g prime at -3. So if I considered a product rule at a given point, one way I could evaluate this is, again, the derivative of the first. We'd call that f prime of 3 because we're now evaluating at the point. And actually -3, excuse me, -3. Times the second function we would just call g at the point, -3, plus f of -3 times the second function at that point. So we're still taking our derivative rules with the product rule, but now we're just evaluating a point in that order. So f prime g plus f g prime. And now we're just evaluating at -3 for each of those derivatives and functional values. So let's go ahead and find those. We do have them listed out here. We know f prime of 3, that's equal to 9. That's given to us. G of -3 is going to be that -4. We have a f of -3, and the f of -3 would be the 12 at the beginning. And then finally we have g prime of -3, which is going to be the 7. So we just use the g and the f here. And we can summarize this a little bit. We have -36 plus, we'll have 84 there. And if I'm doing my math correctly here, that looks to be 48. Looks like 48 is going to be that final. So we have one of them solved. That's looking pretty good. Now, the second one is going to be a little trickier because we have f times h divided by g primed evaluated at -3. So here we're going to have a little more complex derivative to work out, but I think we can do it. So let's dive into part B. I want to kind of approach this in terms of a quotient rule, where we have some f function, f times h function in the numerator, and a g function in the denominator. So in general, what I'll want to consider is we're going to have this f times g is the numerator function. So what we could set out to do here is take the derivative of our numerator in our quotient rule. So we'll just do that in general. G f times h prime at -3 times our g function at -3 minus, we'd have just the f times g function, or f times h function, excuse me, multiplied at -3. And in this case, maybe a little better way to write that would be just the functional value of f of -3 times h of -3 by itself, and then we'll take the g prime of -3. So if I kind of divided these out, this would be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. So those are our four pieces that we're working with. And then finally, after that, I want to, in this denominator, because this is a quotient rule overall, I would want to take the g of -3 quantity squared. So again, with the derivative of a quotient, this is kind of, again, the pattern we're using is the derivative of the numerator, so n prime d plus n d prime divided by the denominator squared. So that's what we're doing, but there happens to be a little quote or product in the numerator. So let's work out this one just a little bit more, because we need to figure out maybe that product that's in the numerator a little bit more. So f times h prime, this first part, I'm going to want to consider doing that. This would really be consisting of a product rule between f and h. So this would say we're going to take f prime of -3 times h of -3 plus f of -3 times h prime of -3. So that is really the product rule that would be in that first position. So if I'm highlighting here, and I'll highlight here maybe in red, this section is just that product rule, all fleshed out. And then let's maybe go ahead and just jot the rest down, and then we'll evaluate these, see if we can fit this in. So we have g of -3 minus, we'll have f -3, h of -3, g prime of -3. All of this divided by our g of -3 quantity squared. All right. If we take a look back at our top of our page where we have all of our functional values and our derivative values, let's go ahead and jot all these in for a final result. We'll start with our f prime of -3. So if we do f prime of -3, that's going to be 9. Times h of -3, that's a new one for us, that's -2. And these are coming from the top of the page. Plus f of -3, that's going to be 12, times h prime of -3. H prime of -3 is 5. And then we're going to multiply all of that times g of -3. So g of -3 here is -4. Subtract. If we subtract away f of -3, that's going to be 12 times h of -3. That is going to be -2. And then finally, g prime of -3 is 7. All divided by, we have g of -3, which is -4, and that's going to be squared. Now, if you do a little bit of work on this to simplify, you can pause the video if you want to simplify this now, but you should end up getting a result here of just 0. So kind of anticlimactic, but this does actually reduce down to 0. So disappointing as it might be, that's going to be our solution for that evaluation. So 0. The next couple questions that we'll consider is going to be taking a look at some tangent line problems. And this will finish us out. The first question says we want to find the tangent of the equations of the tangent line on the parabola f of x is equal to 2x squared plus 7x minus 2 at x equals 1. And this should be just one equation. There should not be plural there, just equation. Let's consider what we would need for a tangent line. So a tangent line is again going to be in the form of y equals mx plus b. So what we need for a tangent line is an instantaneous rate of change, or a tangent line slope. And the way we get that tangent line slope is really to take the derivative set equal, the derivative at the point we're interested in. And this happens to be x equals 1. So one of the components we're going to want is the tangent line slope. So we could call that maybe n tam tangent. That's going to be the tangent line slope we're going to find. And really we're going to find that by taking f prime at 1 in this case, because that's the point we're interested in, f prime of 1. So let's take the derivative f prime of x, and then we'll evaluate it at 1. So if I take this function, we have the derivative of 4x plus 7, 4x plus 7. And evaluating this at 1, we have the value of 4 times 1 plus 7, which is 11. So there's our tangent line slope at 11. Another thing that we're going to need, since I have my slope, I have an x value. I want my actual functional value to be able to create a line here. I need at least a point and a slope to be able to find that intercept. So let's consider finding just the functional value. That'll give us our output at the value 1. So we have 2 times 1 squared plus 7 times 1 minus 2. And if we find that functional value, it looks like that is going to be equal to 7. So we do have a functional value or a point here at 1, 7. So let's consider putting that together. We have a tangent line slope of 11, point at 1, 7. So we can build our line with our slope and our point to find our intercept. And it looks like the only value we are going to need for b, if we subtract 11 on both sides, this is going to be -4 is equal to b. So we have an intercept of -4, slope of 11, and so we could rewrite this line completely as y is equal to 11x minus 4, and that will be our slope intercept form of our tangent line at the point x equals 1. So just to review this problem, we want to consider where our functional value is, so to get an x comma y point, and the tangent line slope at the given point. That'll create our tangent line equation. So let's take a look at a second function to evaluate. We will take a look at a polynomial function this time at x equals -1. So again, the first thing I'm going to consider is finding that tangent line slope. So that's going to require me again to find the derivative set equal to -1 or at -1. So -1 is my input into my derivative. So let's consider f prime of x first. We have -9x squared, -4x, and the 4 just will go away as a 0. And we can continue the process here evaluating. And we'll have f prime of -1. This will give us 9, -1 squared, minus 4 times -1. And so we have, looks like -9 still, plus 4, which is going to give you a -5 as a tangent line slope. So we have a tangent line slope. So the last thing we need to go out and find is our y value here at -1. So we have -3 times -1 quantity cubed minus 2 times -1 quantity squared, and then plus 4. Evaluating this term by term, we have -3 times -1 quantity cubed. That's going to be 4 different negatives. We'll end up with just +3. We'll have triple negative in our second term. -2 times 1, in this case, would be just -2 plus 4. And so that looks to be just 5. We have 5 as well. So our point here is -1, 5. -1, 5. So putting this together into our linear equation, another way we could kind of go about finding our linear equation is putting it into point slope form, and then we could transition that into slope intercept. So let's try that. We know that y minus y1 is equal to my -5 slope times x minus x1. Since x is -1, we would have a plus 1 here. I can distribute the -5, and then we'll add 5 on both sides to balance that equation out. and we end up getting our final equation. That will be y is equal to negative 5x. And this will be our final tangent line equation. So there's a couple examples on tangent line equations. Hopefully this is helpful with all those derivative rules again. You can go back to any of these examples and slow them down a little bit. Take a look at those chain rules and power rule. We did a little bit of quotient rule and product rule in this. So there's a little variety of everything. So in our next video, we will be jumping into a new unit, looking at the second derivative in concavity. So look forward to seeing you in the next video. Good luck on the first exam.